So, in recent years, recurrent and convolutional nets have advanced quite a bit, whereas feed-forward nets have not. Those that perform well are typically shallow and consequently have limited representational capacity. Researchers at the Austrian Institute of Bioinformatics think RNN and CNN training isn't affected by variance in mini-batch samples because of weight sharing. To make linear layers cool again, they invented self-normalizing networks. With the cellular activation function, the output distribution of linear layers converges to a zero-mean unit variance normal, making it easy to train feed-forward networks with hundreds of layers. I want to know whether this extra size makes introducing superstructures in the spirit of ResNext and Inception worthwhile. In essence, grouping parts of each layer together into small towers. Instead of transforming a single 256-dimensional vector into another, could we use 256 16-to-16 vector transformations? This would use 1/16 of the processing power, the same amount of memory, and handle 16 times more parameters. To work well, we'll need to figure out an efficient architecture to combine the towers without confusing our network. Let's take a look and find out what we can do. Good news! It works, and compared our many vectors approach with a self-normalizing network and achieved better performance. Here's the implementation. Our batch linear layer can transform any vectors with independent weights in a single operation. Glue code for FastAI, the library we're using to train our models. Our first attempt at remixing the vectors via weighted averaging. We transformed our 256 by 16 matrix into a single 16-dimensional vector, repeated the operation 256 times with independent weights, and normalized the output to produce samples which fit a zero-mean unit variance normal. Big shout out for HeroPup on Stack Exchange who figured this one out. In theory, this requires the same number of operations as our other layers. In practice, it's 100 times slower. It uses 16 times the memory, which can be mitigated by processing our repeats in sequential batches, but at the cost of more speed. Worst of all, our activation samples actually have a near zero variance, leading to vanishing gradients and no trailing. This could be because of a bug in our code, or it could be because of correlations between features violating the underlying mathematical principles at work. The isolated example works well at least. Our second vector remixing approach is pretty mediocre, but it works. We transpose our matrix, creating 16 256-dimensional vectors, and apply a batch linear transformation. Given multi-block configurations seem less stable, perhaps this vector remixing thing is a bad idea altogether, or maybe a better technique would save us. I'd love to spend more time answering these questions, but we only have 1 week and it's time to move on. Link to the GitHub repository and more on self-normalizing networks in the description. Until later, see you around.